I'd like to thank the User Forum Steering Committee for letting us give regular updates. For ECP, what we'd like to do in these sessions is, instead of a talking head like myself, is have the PIs speak about what's going on. In particular, I'll call that John Turner is going to talk about a key ECP project following me, additive manufacturing. For this update, I thought I'd just give you the bottom line up front. And then I'm going to give a few examples. In particular, I'm going to talk a little about software technology, co-design, and a few application examples. So forgive me, I'm going to fly through this pretty quick. Boy, apologies. I guess I should have tried to figure out a better way. Okay. So just as a reminder, and we've been giving regular updates here, thanks to Earl and company for letting us do this. We've implemented and are executing a pretty aggressive plan, very success-oriented in my view, meaning we're moving out quickly. Oops. We've got a great leadership team in place. We've been working together pretty well as a team. We've got over 100 top-notch R&D teams that have been working now, like I said, for about 2 years. So we're starting to see some great results come out. They've been delivering many milestones. Each of these teams kind of delivers 3 to 5 milestones a year. So we've got hundreds of milestones, many of which are technical reports, software releases. I'll highlight a few here. And as I'll note, most of our application of software products are out there. They're being released regularly and updated. So I'll try to call attention to a few along the way. Currently, we believe we're on track, and I put that in quotes because you never know what kind of surprises we're going to hit, but on track for delivering on our key performance parameters upon arrival of the Exascale systems. We have 4 that we're delivering on. It's kind of 2 are in application space, performance of science and national security apps relative to today, and I'll give you some examples. Broaden the reach of Exascale science, in other words, some new science capabilities. That's another performance parameter. Impact goals and metrics for our software products, and really being able to enrich the HPC hardware ecosystem through our Path Forward program. So we have 4 KPPs, as we call it. In industry, you might call them KPIs. We feel like we're on track. That really defines our success from our sponsor's point of view. We currently enjoy great support from the DOE, and we're a high priority project, which is good and bad. We get a lot of attention, but generally it's great. We're engaging very closely with the HPC facilities. They are not part of our project, but Bob mentioned Summit. It's a great system. We're working very closely with OLCF and ALCF with their systems and enjoying some really nice performance gains. We're really kind of moving more out of the big R, little d phase to product development. Man, maybe it's my computer. Moving more into a product development stage with more quantitative metrics, but still have lots of work to do. Sorry about that. Yeah, maybe. Let me continue. So just as a reminder, the ECI, Exascale Computing Initiative in the Department of Energy, includes ECP, but other aspects. So the system procurements, in this case, the 3 first mover Exascale systems, which I'll talk about, non-recurring engineering investments, facility site upgrades, those are part of ECI, but not part of ECP. And some program offices are also investing in Exascale applications in the DOE outside of ECP. So there are many pieces here, and I'm going to talk about the ECP, which is a part of ECI. So it's confusing, but and hopefully this slide helps a little bit, doesn't hurt. But in ECP, we're about apps, the software stack, vendor R&D, and integration with facilities. And so, not surprisingly, we're kind of structured to really deliver on Exascale-ready apps, a vertically integrated software stack, and leverage US HPC vendor R&D. In the end, we want to really accelerate innovation for the nation. We're going to be targeting key challenge problems of national importance. So our applications are not just building apps, they're actually targeting specific problems. So our success is really not just the application software technology, but the problems we can address and tackle. So we're really signing up for kind of a very focused development activity. Boy, apologies here. I'm getting some really funky. Okay, so the way we're organized, we are a complex project, and we have a hardware and integration focus area, software technology focus area, application development, and project management, which is key for a large project like this. So I'm going to take you through kind of a reminder of what each element does and then focus on just a few examples. So the hardware and integration focus area really is funding vendor R&D in the Path Forward program. Evaluating hardware technology performance, deploying our software stack regularly, early and often to our facilities now, making sure that we're using the pre-Exascale resources adequately currently on the floor, and pushing out applications and testing them. So this is kind of the key sort of handshake between ECP and the facilities, which we really didn't have in place until last fall. Here's our Exascale systems and pre-Exascale system targets for ECP and pre-Exascale systems. ECP here in the United States, we really enjoy a fantastic array of resources. You can see more, the two most recent systems, Summit at Oak Ridge and Sierra at Livermore, are currently going through their last phases of acceptance. And these systems really have far exceeded expectations insofar as ECP is concerned with regard to application performance. So the point of ECP is we're not going to wait to deploy our technology and show its worth via our KPPs when the Exascale systems arrive. We're doing a lot of work right now, development work, targeting the systems and testing and assessing. You can see the TBDs, and these are systems that are currently being, that are under contract or currently being, decisions are currently being made with regard to the hardware and the specifics thereof. But for us, the three systems on the right are the targets for essentially declaring success in ECP and delivering on our key performance parameters. So this hasn't changed in the last year or so. So the hardware and integration focus area, HI as we call it, is really kind of the key handshake between developing our apps and our software stack and then pushing them onto ultimately the Exascale systems, A21, Frontier, and El Capitan, at least kind of the three first movers. But an important aspect is the fact that we're going to be deploying on the pre-Exascale systems, and we started doing continuous integration and testing of our software stack. And again, we should probably have Mike Carew come back. He leads the software area and talk a little bit more about it. But basically, our stack is not the operating system. It's sort of everything above the operating system up to the applications. And so we're deploying these in terms of software development kits already on our pre-Exascale systems. That's really the function of the HI area. Software technology area is divided into programming models and runtimes, dev tools, math libraries, data and viz, and then ultimately pushing out the software development kits. It's pretty complicated. We have 55 project teams executing RD&D in this area, and I'll give a few examples here. One of the things that Mike Carew and team did last fall was recognize that we really needed to think hard about our packaging of our stack and our productization. And so he's come up with a nice concept that he's worked on in the past for math libraries, which is a software development kit. So each SDK has a collection of related components and libraries. Applications can actually dive into an SDK and use one library, but they can also ingest the entire SDK. From an app's perspective, that's really powerful. You can bring in a collection of I/O related functions in one SDK. You can bring in a collection of math libraries and kind of plug and play and try different options. So it's really a nice deployment mechanism. We're going to containerize these. We're going to push them out in an open release, very likely through OpenHPC. We're going to push them and we are also on our facilities. So this is our deployment mechanism and ultimately how we're going to declare success for getting the software stack out there. I'll notice that we've had some interest internationally in, say, contributing to one of the SDKs, which is fine. We welcome the broader community, both vendors and the international community, into delivering their technology through this mechanism. Mike and team did do a really deep dive, broad-end deep dive on our software technologies. I encourage you to go take a look at what we call the CAR, the Capability Assessment Report. There's a large fraction of it that's released publicly on our website. It really is a kind of a tour de force of the 55 projects, what they're doing, their objectives, their milestones, their plans, plan to essentially do this assessment and a deep dive once a year and update twice a year. So this is this will give you a really good idea as to what we're doing and how we're doing it and what our products are planned to be in the software technology area. Let me give a few examples of some milestones now in the ST area. Pavel Blasi at Argonne's been looking at what does HBM buy you. Boy, I apologize for the blurry slides here. What does HBM buy you in terms of point-to-point and one-sided communication? He's finding that it buys you a fair amount for medium and large messages. So in this case, we're all trying to understand and explore just what high bandwidth memory is going to give us. And in this case, there are certain messaging paradigms where we think we're going to get some performance gains. So that's a pretty deep dive in looking at kind of one aspect of memory. Barry Smith has been, pipeline Krylov methods are way cool. It's a way to sort of overlap communication and computation. And in this case, make sure global reductions are expensive. You want to minimize them. Lots of global reductions, think of dot products, min, max, are required in Krylov methods. And so you want to overlap them and not do as many of them as say the normal routine would be. This is known as pipelining. Finding that also, not only in addition to increased performance with pipelining, say a CG method, also being able to have it less sensitive to system noise. So Barry will be delivering these technologies through his widely used PETSI library. So this sits kind of in our math SDK. Jack Dungera is just a rock star in this community. His new library, software for linear algebras targeting Exascale or Slate. You can see the design at the top. Really sits kind of on top of a BLAS and LA pack. He's redesigning it with DAGs and task-based runtime system known as Parsec. And the apps sit on top. In this case, Exalt is a material science application in ECP. And so one nice thing about having an Uber project with all the PIs working together is we not only work separately on our own products, but integrate them into others. In this case, Jack has integrated Slate into Exalt, which is a molecular dynamics application that comes out of Los Alamos. So here's an example of a Slate release as well as integrating into an application. Cocos is a very nice abstraction layer that comes out of Sandia that's really been widely adopted and used now in our application portfolio. Essentially abstracts the memory hierarchy and CPU hierarchy. And it's a C++ based library that lots of applications are using. We're finding that the more we train people about how to use this, the more people, Cocos, the more people are embracing it. So this is an example of a training activity which is very important in ECP, not just external, but among the teams in ECP. And think of like a for-all loop that's now overloaded to say, okay, this is a GPU, I know how to do this in a better way. Or I'm going to lay out a 1 or 2 dimensional or 3 dimensional array, and Cocos is going to black box and lay that data out for you based on the hardware at hand. So it's a nice abstraction that a lot of applications are using to our we're really pleased to see that. Application area, which is one that's more near to my heart, includes 25 different application projects spanning kind of the domains you see in co-design. I haven't talked as much about co-design in the past, so I want to mention talk a little bit more about co-design. In our philosophy, and co-design is an overloaded term. It means a lot of things to a lot of folks. And in ECP, we are doing co-design kind of all the way application through software down to hardware. But in this case, the co-design centers that sit in the application space are really co-designing more in the software sense, working down through the compilers and the runtime systems, and focusing on application motifs, which is essentially the app footprint on the platform. So think of a motif as a common pattern of computation and communication, and these are the 13 that Berkeley's published about 10 years ago. And you see the 6 or so on the right are more data analytics motifs, and the classical motifs on the left are the ones that we think more traditionally for deterministic mod sim. The point is in ECP, we're targeting these motifs. Not all of them, we don't have the time and the resources, but a lot of the key motifs. You can see when you do a mapping of applications, typically an application will use kind of a 3 to 5 of these motifs, not all 12 or 13. You notice too, machine learning tends to use the data analytic motifs, so we've got a little more sparsity on the right. This is just an example of kind of a matrix in terms of who uses what. So our co-design philosophy is to target these motifs that are most impactful to our applications. And that's led to some centers, okay, and our co-design centers, you can see everybody likes crazy acronyms, CODAR, COPA, AMRX, SEED, Exagraph, and we just added a new one for machine learning, ExaLearn. So we currently have 6 co-design centers. We're likely to not expand as we move forward, although I'll note that we do have some FFT efforts that we're not really calling a co-design center, but essentially functions as that in Mike's area. So I want to call attention to just a couple of the co-design efforts. The ExaLearn Co-Design Center is one we've just stood up. It's PI by Frank Alexander at Brookhaven. And you know, I think it'd probably be good to have Frank and team come back and give you an overview. They've just started, and they have some pretty aggressive goals. And you can see overall here what we want in ECP is a tool set. We don't necessarily just want best practices for essentially how to go after sort of key research areas in machine learning, but we want a tool set that's applicable to multiple problems in mission space, as a line of sight to some of our applications, and in particular looks at our experimental facilities where scientific images are flowing off our multi-billion-dollar facilities, and we can do a lot better, I think, in getting return on that data. So probably the low-hanging fruit is scientific image analysis. But this team has identified areas in need of research, in particular physics-informed AI, verification and validation of the machine learning decisions that are being made. DARPA has an explainable machine learning program we like, and so we're going to be kind of looking at that as well. And performance and scalability. You know, I think we've seen, Bob mentioned this on Summit, a sort of 2 exaop application with half precision. So we've seen scalability from a data parallelism point of view. It's the model parallelism that's the challenge, or spreading the network, the neural net across the machine itself. So, you know, stay tuned for this one. We expect to hear more, to see more interesting results and technologies come out of ExaLearn. I want to say a little bit about CODAR, which is the Center for Online Data Analysis and Reductions, led by Ian Foster at Argonne. It's focused on kind of a key aspect, which is workflow. And in this case, we want to be able to do in situ analysis and reduction of the data as the applications are running. And see the overall architecture here. There are kind of 2 key pieces that Ian and company are releasing, and one is called Cheetah, which is the experimental harness, and another one's called Savannah, which is the runtime infrastructure. You can see the overall architecture. You know, these releases are out there, and in particular, they're testing this workflow, which is really kind of based with Swift, which is a nice workflow language, in several different applications, nuclear fusion, cosmology, turbulence, in this case, both climate and combustion. And apologies for the blurry slide here, but this is examples of doing real-time detection, in this case, in fusion, trying to detect turbulent areas, and cosmology, looking at halo detection. And so these are the sorts of things that application people kind of done on their own. And now we're going to have a workflow environment to essentially help the applications do analysis and reduction of data in situ. Another, boy, really apologize here for the blurry slides. Another really, really important co-design activity for us is adaptive mesh refinement, led by John Bell. And this is called AMRX, and he's also got several releases already out there, but many of our applications use structured block-based approaches for their meshing, and many have rolled their own in the past in terms of adaptive mesh refining. By having one co-design center focus on this technology, and it's not just you know, multiple patch AMR, adaptive mesh refinement, but it's how to do linear solvers on these types of grids, multiple time stepping approaches. You can see pushing particles on the grids. And so in this case, AMRX kind of embodies several different motifs, not just mesh refinement. A number of applications are already using AMRX, and again, you can't see it up there, but cosmology, combustion, multi-phase flow, astrophysics, or just to name a few. So this is a key co-design activity. The framework's already has been pushed out there. Here's examples, and I know there's going to be some talks on combustion here, and for the audience here today, maybe in the automotive industry. We do have a combustion application that's taken advantage of the AMRX co-design center. In this case, one approach to doing complex geometries is to use the structure mesh and cut the cells, so essentially cut out the complex geometry, from within a more structured mesh approach. And the advantages there is you can be fast on your feet with regard to geometry, really reduce the meshing time. It's sort of runtime meshing in sense with cut cells. And also you can get very, very effective and fast utilization of the hardware. And so here John and his team will work really hard on making sure they can do the embedded boundaries correctly, get the shock reflections, be able to have the refined meshes track the interesting features in the flow, in this case contact line discontinuities or shocks. And there you can see really important work to be able to mesh refine these features dynamically. So you've got mesh patches and tiles that are moving with the dynamics of the simulation. You want to be able to break the mesh up into small tiles and thread them off onto a GPU. And so there's lots of important details with regard to being able to do this efficiently. Another important co-design center now moving to another, kind of the other meshing paradigm, which is unstructured meshes. We also, and this is a key motif, we also have focused very hard on being able to implement libraries for finite element discretization of PDEs on unstructured meshes. And this covers a wide number of applications as well. And you'll probably, I think, going to hear more about NEC, which is a key application for us. This is led by Zanio Kothe at Lawrence Livermore. And the idea here is to really, especially with accelerators like GPUs, to really go after a higher order. Now you've got flops essentially for free, and you can do 4th, 5th, 6th, 7th, 8th order essentially for the same price as 2nd order. And that also allows you to use less mesh, which means less memory. And so it's a good mapping for where we're headed in Exascale, which is lots of compute and not as much memory as we'd like. So for multi-physics approaches, going higher order and using a library that this team is putting out, known as LibSeed, is we think going to be very, very advantageous for our unstructured mesh applications. We're seeing really good returns already. So this co-design center, known as SEED, is releasing its technology, and SEED really consists of a finite element library. And well, actually, on the next slide. Well, here, let me just point out that John Turner's application, additive manufacturing, known as Exam, is looking at the SEED co-design center. But think any unstructured mesh application is going to be able to take advantage of this technology. Again, finite element-based unstructured mesh approaches. SEED itself consists of about 12 different packages. In particular, libraries for finite element operators. They're trying to standardize the way you lay out, meshes like this. And so a lot of work's gone into really trying to instantiate everything that it takes to do high-order discretization on finite element meshes. LibSeed is and these are examples of milestones that are coming off the teams. So you're seeing, again, releases and demonstration of performance as well as technology. So really wanted to call out, this is kind of one of our shining stars in terms of our co-design efforts. Really what we see in co-design in terms of efficient high-order discretization on unstructured meshes. So moving on now, kind of through the application portfolio, and I just want to call out a few examples. So again, we have 25 applications in ECP, and the teams kind of range from 4 or 5 to 20 or so. 22 are in kind of DOE Office of Science and Applied Energy space, actually 21 of them. One is an NIH application for precision medicine for oncology. That's very much a machine learning application. And then 3 are national security apps. So in particular, I want to say a little bit about the small modular reactor application, because it really shows kind of what we're seeing now on machines like Summit. So one challenge is, if I've got a lot of data locally, in this case cross sections, how do I take advantage of the non-volatile memory? And they've come up with a windowed multipole method to essentially kind of recompute the cross-section data on the fly rather than store it. So that's a key design feature. And as a result, they've been able to show, and you can't see it up there, but they're pushing almost, this is a Monte Carlo method, almost 300 million particles per second on Summit because of the GPUs. And that gives them a kind of a figure of merit, which is a ratio of performance on Summit relative to Titan. That's kind of our baseline of close to 40. And that's fantastic, because for a lot of our apps, we're targeting 50x performance, and we're seeing Some of our apps are already at 30 or 40 on Summit. And it's not just the hardware, but it's what we're doing with the hardware and redesigning algorithms. And in this case, NEC 5000, which is really important for combustion and a lot of both compressible and incompressible flow simulations on unstructured meshes. They're using the SEED co-design center as well. But we're seeing here on Summit GPU acceleration, order 5x already. Think we can get another 4x, and so now another sort of 20x throughput just moving from Titan to Summit. And this is what the GPUs are giving us. In particular, the Volta has a lot of nice features. Kind of walking you through our application portfolio, I'm just going to hit a couple examples, but just as a reminder, we've got clean fossil fuel combustion, and that's multi-phase flow. We've got chemistry, biofuel catalyst design, materials for extreme environments, so that's molecular dynamics, and essentially using replica exchange to do long time integration. And additive manufacturing, John's going to tell you a lot about that after me. Quantum materials, hopefully some of the PIs can come back in this venue for those, that if you're interested, and we can give kind of a deeper dive. So let me say a little something about combustion. This is led by Jackie Chen at Sandia. So she's got her team, as we've released 2 new codes known as Pele, because she's a soccer fan. Pele-C for compressible, and that's a compressible DNS code, and Pele-LM for a low Mach number code. In this case, she's using the AMRX co-design center to do adaptive mesh refinement of combustion flows, in this case targeting the RCCI concept, and showing she can do embedded boundaries, and she can push particles. In this case, she's using particles for Lagrangian spray model, and so she's also going to use it for soot modeling. So here just using the AMR machinery for mesh refinement, but also for embedded boundaries and pushing particles. So the Co-Design Center AMRX works very closely with this new capability. So again, the Pele code suite has been released and continues to evolve. This is an example of kind of a brand new capability that's rolled out because of ECP. We've got climate change applications. We have chemistry, metagenomics. I think some of these have come to this forum and talked. Cosmology, QCD, plasma Wakefield accelerator design, lots of a whole device model for fusion and astrophysics. Again, just to kind of remind folks in terms of what we're doing. And I'll note that what I have here on these slides is sort of the challenge problem that they're targeting. So we're not after just generic capabilities. We want to target specific problems and the impact of those problems if they're addressed and potentially solved. I mentioned the healthcare application. We've also got an application that's very much event-driven, focused on light sources, in this case, the LCLS at SLAC. So kind of to summarize our flow of product delivery and deployment, we've really defined an ECP. We've got, in our software technology area, order 90 different products that we're developing, package them into order 6 SDKs, or software development kits, push them on to our facilities today on the floor in the DOE, continuously integrate, test, release. So this is more of an agile approach, or a release early and often, get continuous feedback from the users, and refine the requirements. Develop APIs for the applications, and also push applications on not just the Exascale, but pre-Exascale, so we can begin to do our science tests and performance analysis. So that's kind of our product delivery flow, which was kind of really crystallized over the last 6 months or so. Just a few notes. We've recently appointed Laurie Dyson as our Deputy Project Director. She replaces Stephen Lee, a good friend and colleague who retired from Los Alamos, in my view, many years before he should have. But I guess because I'm a little jealous. But Laurie's a fantastic addition. I also want to call out, Susie Tishner and Dave Martin are always here at HPC User Forum, and they play a key role for ECP as co-executive directors of our industry council. And Dave Kapczynski is also here, and he is our chair. So this is really a key interface for us to industry. We're really interested in what problems you would like us to solve. It's an advisory body. I'll point out it's not a formal review body. But we do want to seek your advice. And in particular, we're targeting HPC users and developers on the industry side. So I encourage you to talk more to Susie and Dave and and David throughout this meeting. So that said, 9:47, so I didn't do too bad. Anyway, thanks for your time and attention.
Hi, my name is Francisco Artigosa from Repsol. I have one question. Sorry for my ignorance.
That's okay.
It's absolutely great that you have so many applications. So who are the users? These are open source applications, they are commercialized. Who are the users?
So for the most part, some of the applications are not open source, but for the most part, most of them are. And each of the applications points to a specific Department of Energy program office. So the stakeholders are, the problems that we're tackling are driven by our Department of Energy mission. Users range from people just working in that program to a broad audience. As an example, one of our codes is called Games. It's a chemistry code. There are 120,000 users worldwide. Other applications are not released and really just used internal in Department of Energy.
For instance, my company as an oil company, we can make use of that software or not? Yes?
Yeah, so a commercial software company could pick up the application, could ingest it into its own proprietary workflow. Most of our applications, when they're released openly, are released under a BSD or an LGPL license to allow that kind of thing. So we really want to work hard to get our technologies out there.
Okay, thank you.
Sorry.
I think there's a couple more questions.
Okay.
I'm just switching.
This is a quick one. Rich from InsideHPC. Doug, a question about the ECI. A lot of confusion between that and what you do is ECP, right? Okay, ECI, why is it so hard to find information on what, because there's no website, there's nowhere to, there's no link, there's no Wikipedia, nothing.
Yeah. I'll take that back to my sponsor, Rich. No, I don't disagree. It is confusing because the acronyms only differ in one letter at the end. But I will note that for ECP cannot succeed without these systems in the broader ECI being deployed. And so each of the three platforms I mentioned, A21, Frontier, and El Capitan, are separate formal projects, in fact, but we are joined at the hip with shared milestones. So we all succeed or we all fail. So ECI is really